right, just we will see about the trends in cost, because this also matters, right? Like whenever just we are going to purchase anything, probably, right, we need to be worried about the cost. At the same time, right, two important is, one is we need to have a lower cost, and at the same time we need to have a performance. The performance should also be increased. So it is very important for understanding the cost and its factor for design, to make an intelligent decision by the computer architects. So this is very important. The cost has to be lower, at the same time the performance has to get meet out. So in general, right, there are few impact that may decrease the cost. So the one is the time, the next one is the volume, and the third thing is the commoditization. So what is that? So first we'll just go for the time. So this is the time. Uh, so whenever, right, we are going for manufacturing the computer, so probably, right, the computer component is decreases over time. Even, right, whatever, suppose, right, 10 years back, if you are implemented with some technologies, and the same component, if you are again after 10 years, if you are trying to sell, so definitely, right, the price will be decreased. So what they are saying is, over a period, so the cost, the manufacturing cost will decreases over a time. So that they are saying it as learning curve. So the learning curve is the best measured by change in the yield. So the learning curve is which means what it says is, right, the manufacturing cost, it decreases over a time. Clear? Um, so this is also important. So the designs that have twice the yield will have half the cost. So this, you know it, right? So whenever you have twice the yield, probably, right, you may have half the cost. So always, right, when you just go with the cost, it is closely associated with the time. That is very important. So the cost of the any component, computer components, will decreases over a time. So that they are saying it as a leaning curve. So that is the first things. The next one is the volume. So this also, you know, right, whenever you are designing any component, probably, right, when it is in a something in a huge volume, so probably the cost may be less. So this is a rule of thumb, right? It's quite common, right? We experience the same thing, right? When you purchase a single, so it may be some amount. When they says, right, if you purchased as a 4 or 5, there may be less in cost. So the same thing is applicable here also. So the cost will decrease about 10% for each doubling of the volume. So this is the second important factor that decreases the cost. And next one is the cost of an IC. So when you just go with the cost of the ICs, if you take any ICs, I think these are all the base things that are essential for designing the chip. A wafer is there, and it is chopped into dies, and the dies are packaged. So this is the formula for designing an integrated circuit. The cost of the die plus cost of testing die, cost of packaging, and final test, the whole divided by final test yield. So this and all, just you just keep remember. Okay, so when you want to decide the cost of the ICs, so these are all the things. And again, when you just go with the cost of die, which is equal to cost of wafers divided by dice per wafer plus dice. So this part, so this will be the wafer, and these things will be the dice. So cost of die will be the same things. Also I'm repeating. So whatever the formulas they are given over here, uh, you just please remember all those formulas. What will be the cost of integrated circuit? What will be the cost of side die and the dice per wafer? Okay, these three formulas you just please remember. So based on that, they may give a problem, and you might be in a position to substitute, and you have to find the answer. Okay, so it is there in our textbook. We just kindly go through these problems. Okay. Um, okay. So this is for the cost of the ICs. And similarly for die yield also, you take this formula. I think one more topic is missed out. One is the time, volume, and I told you this commoditization. Commoditization is something like, see, if suppose if you have a memory or any component, probably right, you may have like multiple developers will be there. So there are many people who are onto developing the same product. So ultimately, right. So for that competition, what they will do is right, they will try to reduce the cost. So that is about the commoditization. So what they will do is right, we have multiple manufacturers for the same components, and right to make their profit, they will try to reduce the cost. So ultimately, right, the component cost may be reduced. Okay, so these are the three factors that may influence the cost. So the first one is the time, the second one is the volume, and the third one is the commoditization. So time is, so any component over a period, it will decrease. Okay, so that they are saying it as a learning curve. Next one is, sorry, learning curve. The next one is the volume. Whenever, right, we are just if the volume has been uh, will be reduced. And the third thing is commoditization. Here, right, we have multiple manufacturers who are developing onto the same components. In such case, also cost will be reduced. Okay, so these are the three important factors that have been associated with this. As a tumor, they put a question on this, like what are the important factors that may influence the cost? This is one. And the second type of questions that you may get it over here is this part. So clearly, right, when we give these values and they ask you to calculate what will be the cost of integrated circuit or cost of 10 dice per wafer. So please thorough with these formulas, and because right now it's not a time to derive these formulas. So just remember these formulas and you may get a problem on this. So only these two questions you may expect in this topic. Shall I move to the next one? I think I'll add this commoditization topics. I don't know, I forgot to put, I studied in the textbook, but I forgot to put it in the slide. Shall I move to the next one? See, this is what I'm saying. Till Saturday, right, it will be something like a theory kind of things. So from Monday onwards, I mean, it will be interesting. Okay. The next topic is dependability. Yeah, listen again. I'm insisting with this first chapter, whatever there in the slides, because I'm parallelly I'm posting the slides and also the materials. This is more than enough. Just by looking onto the books, right? I mean, you have the. I mean, I forwarded the textbook link also. If you want, you can. I mean, I'm not discouraging that. Don't go for that. But if you start study, right, you may feel something hard or something. You may feel that. So, as far as first chapter is concerned, you just go with these slides itself. You can. I mean, as exam point of view, also I'm saying you won't get. What to say, big questions on these topics. So preferably 2 marks. So every slides, I'm just trying to say what type of questions you will get on this topic. So just kindly note down only those kind of questions you may get over here. The only possible big questions in this is that one, the defining the computer architecture. So in that we have seen with respect to instruction set architecture, right? So that's 7 points. So maybe right, they may ask you to elaborate those things as theory questions. Okay, so the rest things will be a formula oriented problems. So if you want, right, I will try to post the first CA questions. You just kindly check it out. So how it is going to be. So accordingly, just try to prepare for your exams. And the next Saturday, you will have a test on chapter 1. Okay, it's going to be a common test next Saturday. 4th, you will have a test. Okay, so the next one is the dependability. So here, right, dependability, it's all about the two metrics. One is the reliability, another one is the availability. So these two are the important metrics when you just go with the dependability. So in general, right, when you talk as dependability is the quality of the delivered service. Okay, so I mean, so hope you understood this, right? So it's a quality of delivered services. So generally, right, whenever delivered, right, okay, suppose a system alternating between two state of delivered service with respect to service specifications. We have two states. One is the service accomplishment, another one is the service interruptions. When you go with service accomplishment, service is delivered as specified. So whatever we require, the same thing has been delivered. So that's not the problem. So when you go with service interruptions, delivered service is different from the specified service. So maybe, right, it is not meet out the performance. So they say from state 1 to state 2, it has been delivered properly. Later, right, we have some failures. I mean, if there is a transition from state 1 to state 2, it is caused by failures. Suppose, right, if there is a transition from state 2 to state 1, it is called restoration. Because, right, because it is not in specified service, and again, right, they are trying to change it out. So this is the restorations, and if that is from state 1 to state 2, it is going to be a failures. Okay. Yeah, this is what I told you. So when you just go with what is the dependability? So two important factors. One is the reliability, another one is the availability. So these two are the important factors here you have. So one is the reliability, another one is the availability. So what is reliability is the mean time to failure, which we say it as MTTF. Okay, reliability is mean time to failure. So rate of failure is the reciprocal of MTTF. So I mean rate of failure will be the reciprocal of reliability, mean time to failures. Clear. So if suppose if you have a service interruption, so I mean when you have a service interruptions, which is referred as mean time to repair, MTTR, because I mean we have a service, so probably, right, we need to go for a repair. So mean time between failure, so this can be calculated as MTBF is calculated as mean time to failure plus mean time to repair. So when it has started failure and it is repaired, okay, so that time will be your mean time between the failures. So that part we are just I mean, it is mean time between failures. So remember this. So mean time, what is the time between the failure is when it started failures and when it is the time to repair. So between that will be your mean time between the failures. So these are all the things that have been associated with reliability. One is what? Reliability is MTTF, and the rate of failure is equal to 1 by reciprocal of MTTF, okay, and mean time between failure is mean time to failure plus mean time to repair. Okay, so these three things is associated with reliability. And moving on to availability, okay, it is the service accomplishment with respect to the alteration between the two states. So accomplishment and also the interruptions. So let me go here. So this one. So module availability, you can write it in terms of this. Mean time to failure divided by mean time to failure plus mean time to repair. Okay. So these four formulas, please remember here. So one is what? Rate of failure, which is the reciprocal of MTTF. The next one is mean time between the failures. It is MTTF plus MTTR, and the module availability is MTTF divided by MTTF plus MTTR. Okay, so these are the three formulas with respect to reliability and availability. Now, right, we'll just take a problem, you have a disk subsystem, the following components. We have 10 disks, each rated at some time for failure. One attack controller, one power supply, one fan, and one attack cable. We have these things. Okay, and they given at these times, there may be a mean time to failures. So using the simplifying assumptions that the lifetimes are exponentially distributed and that failures are important, they ask you to compute the MTTF of the system as a whole. So this is what the question is. Okay. They ask you to compute the MTTF of the system as a
Ma'am, your voice is breaking, ma'am.
sorry. Okay, so now to compute this MTTF, mean time to failure. So they are given the mean time to failure for the individual systems, and we need to compute the mean time to failure for the entire system. So this what the problem is. So what we need to do is, so first they are going to calculate the rate of failures. So I mean this failure rate, you know it. What is failure rate? Just now I discussed it, which is nothing but the 1 by reciprocal of MTTF. So failure rate will be 1 by reciprocal of the 1 by reciprocal of MTTF. So this is for this 10 disk. So according to this formula, okay, 10 disk, one attack controller, one power supply, one fan, and one attack cable. So they did this. So 10 into 1 by this, 1 by this, 1 by this. I mean, this is what they are given MTTF for respective components. Okay. So by that, right, they calculated the failure rate. Okay, so this is the failure rate for a system. Okay, so we know that, right? What is MTTF? MTTF is the again it's a reciprocal of the failure rate. So I mean 23,000 divided by these things. So just we are taking the reciprocal. So when you just try to do is approximately we are getting like 43,500 hours, which is equivalent to 5 years. So if if any component which is rated at, I mean, if they given the mean time to failure and they ask you to compute the MTTF of the system as a whole, so what we need to do is we have to find the failure rate, and from that we have to find the MTTF, and you need to get the results. So approximately, right, it may take 5 years to failure. So I mean they concluded, right, it may take 5 years to conclude. So one is I mean to avoid failures, this is a normal thing, right? So one thing is, right, we need to go for a redundancy. So whenever you have a redundancies, probably, right, the failure may be reduced. So this one clear. So this is there in dependability. So again, I repeat. So when you just go with the dependability, it is all about the quality of the delivered service. Generally, two states we have. One is the service accomplishment, another one is the service interruptions. So you know it, right? From state one to state two, it is failures, and state two to state one is the restorations. And for dependability, you have two major metrics. One is the reliability, another one is the availability. So for reliability, you know MTTF, and right, reciprocal of MTTF is the rate of failures. Similarly, mean time between failures is mean time to failure plus mean time to repair will be the mean time between the failures. The next one is the availability, which is mean time to failure divided by mean time to failure plus mean time to repair. So the problem what you may expect in this topic is this one. They may give the individual MTTF for each system, and they ask you to calculate the MTTF for the entire systems. So what you need to do is you have to calculate the rate of failures, and once you calculate the rate of failures, so probably reciprocal of that is going to be the MTTF of the whole systems. So by that you can find out the MTTF. Okay. So this what is in dependability. Till lecture 9, it will be like this. First, I will finish up this. Okay. Okay. So the next important parameter is performance. Okay. I think in the beginning we talked, right? As we are given concentration for an ISA, and then right we just slowly move to the cost, this dependability, and the technology, and finally performance is also a matters everywhere, right? So that is very important. Again, it is depends upon that classes of computer what we are going to use, because when you take a desktop computer, so they may be interested in reducing the response time, probably the execution time or latency or any. Okay, latency majorly, right? This is going to be the latency with respect to desktop users. When you go with the warehouse scale computers, there it is interested in what throughput, how many requests have been processed so far. Okay, so that is with respect to warehouse scale computers. But when you just go with the desktop, here, right, I mean, the performance is with respect to the reduction in the execution time. So this one, suppose they are given like this: X is n time faster than Y. If you have this, I mean, if you want to have a ratio between this, so execution time of Y divided by execution time of X. And performance, again, execution time is the reciprocal of the performance. So if that is the case, 1 by performance of Y by 1 by performance of X, which is equivalent to performance of X by performance of Y. Clear? So this one, right? When you want to compare two processor, say X and Y, so this is what we need to do. So that is the execution time of Y divided by execution time of X. When it is in terms of performance, so it should be as performance of X divided by performance of Y. Okay, suppose if you have a statement like this: throughput of X is 1 by 3 times higher than Y. So what that statement says, the number of tasks completed per unit time on computer X is 1.3 times the number completed on Y. I mean, this is what it is. So when, I mean, if X is 1.3 times higher than Y, means it says that X is 1.3 times the number completed on Y. Now the question is, okay, when you just take the desktop computer, we are speaking in terms of execution time. How will you measure up the execution time? So that's the question, right? Because many things has to be taken into account when you are going for measuring the execution time. Because assume that I'm executing something, uh, sometimes, right, the program may be depend on memory, or it may be depend on IO devices. So many parameters are there. So that's what they're saying here. It may have a disk access or a memory access or input output activities or some OS overhead, everything will be there. This all comes under execution time. Okay, so again, right, this is, I mean, these things are nowhere related with the CPU aspects, right? So when, suppose, right, if I wants to know how the CPU is going to perform, these things are nowhere related with the CPU aspects, because it is purely assume that memory access device, the speed. If you take a CPU and if you have a memory, so probably, right, the speed of the CPU will be greater than this. Means speed of the CPU will be greater than the speed of the memory devices. So assume that if it is going to complete in one cycle, the memory to fetch the data from memory and send it to the CPU may take 5 clock cycles. So what is happening? If the data is there, the CPU will complete in one cycle. Since it is going to depend upon the memory, so probably, right, it may take additional time for this. So with that, we cannot measure the efficiency of the processor. That's the one thing. That's the major thing. So what they say, and also, right, when you just go with the multi-programming, the processor is works on other program while waiting for IO. So what is this statement is? Okay, with multi-programming, assume, right, we have P1 and we have P2. So when it is multi-programming, what will happen? What do you mean by multi-programming? it's a kind of overlapping. So which means, right, P1 is in execution, at the same time P2 will be there. So when P1 is waiting for some IO activity, so meanwhile, right, P2 will get started. So I mean, it will be executed in an overlapped fashion, but it gives us a illusion as if, right, both are running in parallel. But actually, it is not running in parallel, but it is trying to execute in overlap fashion. So many things has to be considered when you go for defining the execution time. So to avoid that, what we have to take into account is we need to find only the CPU time. If you want to estimate the performance of any computer, the only parameter is we have to identify the CPU time. I mean these times and all. So for discussers, memory access, for input output, how long it is wait, those things should not be taken into account. Only the code whatever we are given, for that how much time it takes. So by that only we can able to evaluate the performance of any processor. So this is what they're saying. The CPU time is the time the processor is computing. It is not including the time waiting for IO or other running programs. Okay, so only with this only we can able to estimate the performance of the processor. So now the question is how to evaluate that, how to estimate I mean the performance, the CPU time of any architecture that has been developed. So probably, right, what we need to do is we have to take some set of workflows and it has to be executed on that machines, and by that we have to estimate the performance. So I think this what you might have heard, which is nothing but the benchmarks. So what they will do is whenever, right, any computers, any architecture has been designed, you have some set of benchmarks. So those benchmarks will be executed on those architecture, and accordingly they will estimate the performance. So again, the benchmarks may vary, depends upon the classes of computers. For desktop, they may have some kind of benchmarks, and for supercomputers they may have, and similarly for variable scale computers, and for suppose if you have a database applications, so for that they may have different kind of benchmarks. And suppose if you have IO, only IO activities is there, how it will be performed. Okay, so different kind of benchmarks are available. So based on those benchmarks, we need to estimate the execution time. Clear? So for that, right, I told you the different benchmarks. The benchmarks that which is nothing but the programs, different programs. One is which they are saying just kernel. So when it is a kernel, which is a small key pieces of real applications. Say for example, suppose, right, a fast Fourier transform. So this is a real-time application. So what they will do is, right, these applications will be executed on all the machines and they will try to estimate. So when they talk as a kernel, it's just key pieces of some real-time applications and they will try to execute that application and try to estimate. Or is the toy programs. So hope you know these toy programs, right? Which are what? Some 100 lines of programs from beginning programming assignments such as quick shot, some program, or else, right, say like as we are doing it, like printing the hello world, it's also a kind of toy programs. Okay, so similar kind of programs they may give, and they may try to estimate the performance. Others, right, synthetic benchmarks. So here, right, which are all some fake programs, so which is invented to match the profile and behavior of real applications. So some fake programs will be designed, and that fake programs should be executed on the processor. This Diastone is one of the type of benchmarks. So you have plenty of benchmarks. Okay, so whatever the kind of applications or whatever the classes of computers we are going to choose, accordingly, right, it has to be delivered. But normally, right, the compiler writer and architect can conspire to make the computer appear faster. Because I told you already, right, whenever a computer architecture has been designed, compiler is the first system software that is going to get developed. So they can do anything. As if they give an illusion, right, this computer is going to work faster. But there are few parameters that has to be done to avoid this kind of, what to say, false approach. So when you just go with the benchmarks, three things they are saying. One is no source code modifications are allowed. If they are designing, assume that they are designed an FFT applications, it shouldn't be modified. It has to be executed as if on all the systems, and you need to evaluate the performance. Or else source code modifications are allowed, but are essentially sometimes it may be impossible, because when you just go with the database benchmarks, so it is relying on standard database programs. So such cases we cannot do it. And third case is we can modify the source code, but as long as the modified version should produces the same output. So again, these are the three different approaches with respect to the benchmarks. So most of the cases, right, they will go for this. So they may have the benchmarks, and without any modification, those benchmarks has to be executed on the systems, and they need to evaluate the performance. Okay. So if you just go with the benchmarks, right, there are many benchmark suite available, depends upon the applications. Again, this is the theory part, but just keep remember these names. So one is EEMBC. Okay. So Electronic Design Embedded Microprocessor Benchmark Consortium. This is a one type of benchmark which consists of 41 kernels. Just now we have said, right? What is kernel? It's a set of real-time application programs. So since it is for embedded applications, it may contains for automotive, industrial, consumer, networking, office automations, and telecommunications. So the different kinds of applications will be there over there, and they will execute those kind of application in that processor, and they will try to predict the performance. Okay. So this is main EEMBC is majorly for embedded applications. And similarly, you have SPEC, Standard Performance Evaluation Corporation. This is also another kind of benchmarks. So this kind of benchmarks is for workstations, and even for desktops also. I mean, for remaining case also it may work. When you just go with the desktop benchmarks, they're just trying to classify as processor benchmarks and graphics oriented benchmarks. And these are all the different benchmarks names. I mean, I just keep remember these things. That's enough. So, what are all the benchmarks that are available? But here they haven't specified. But in general, as I listed out already, they will classify like this, like a processor benchmark, system benchmark, IO benchmark. This is the major cases we have, and database. So all those things, right, maybe fall into any one of the categories. Okay. So the only thing is, like, you just have a differentiation. EEMBC is for embedded applications, SPEC is for the workstations, and again some variations. SPEC CPU 2006, 2095, 92, and 89. Those are all for the desktop. Similarly, for the servers, also the SPEC. It is also a kind of benchmark that is available. So I mean, we can execute and it just you see it. Okay. Um, and again, even when it is server kind of things, the variant rate they are going for this thread level parallelisms, and spec offers high performance computing benchmarks around open npmk. See, my thing is that you no need to write any code, anything, so it is readily available. Simply we need to take that code and it just execute and it just visualize the result. If you want, you can even you can do it in your systems, and you can have a just comparative analysis how it is going to get works. Okay. So because they may give some standard parameters will be given, so after executing they may give some parameters. So with that we need to compute, I mean with that we need to estimate the performance. Okay. Again, this is for this network file systems. Again, for web bundle we have spec web, and this is transaction processing is for a database kind of systems. Whenever, right, we have a database access and update, such cases. So these kind of benchmarks has to be evaluated. So all those things are the examples. TPCC, HEE, just kindly have a look onto that. Okay. So I mean, so this what with respect to the performance. Just when you go with the performance, so it is all about the execution time. So again, it depends. When it is a desktop, it is execution time. When it is backlog scale computer, it is going to be the throughput. And when you want to compare the execution time between two processes, it may be like execution time of X by execution time of Y. And if it is a performance, reciprocal of the executions, right? So you may get the performance, these things. And now the question will be how to determine the execution time, because there are so many parameters which may influence the execution time, but we need to take only the CPU time. So what is CPU time? The processor computing, and it should exclude all the waiting for IO, running other programs. All those things should not be included. So that we are saying it as CPU time. So when you are going for really evaluating the performance, what we need to do is we have to take some set of programs, and that program has to get executed on that processor, and we need to evaluate it. So they are just saying with three different types. One is the kernel or the type programs, or it may be a synthetic benchmarks. So kernel is the real-time applications, type program just for, you can return by yourself and you can execute, or some benchmarks will be available and you can take it up and you can run it. So when you just take the benchmarks, if you take something as benchmark, it shouldn't be modified. Even if it modified, it should produce the expected result. That is very, very important. So next one is the various benchmarks. So depends upon the applications, we have to choose the benchmarks. So we cannot run the same program for all, all oriented, all kinds of applications, because for desktop it may be different, for server it may be different, for transactions it may be different, for IO it may be different. So accordingly, we need to choose the benchmarks and it has to get executed. So in this, after this benchmark, you just try to learn the name of the benchmarks. For what kind of application, what kind of benchmarks can be used. For an example, this is not like something knowledgeable. Just learn the name of certain benchmarks that are available. Okay. So any doubt in this? Okay. Is it visible?
Yes, ma'am.
I think this is the last topic in chapter 1. Quantitative principle of computer design. And right here we are going to discuss these 5 topics. One is the parallelisms, principle of locality, common case, Amdahl's law, and the processor performance equations. And again here right we have a problem on these 2 topics. So you may get a problems on these 2 topics, and this is like 2 marks kind of things. Okay. So again, these are also associated with the performance improvement. Okay. So how to improve the performance of a systems? So here, right, the first way to improve the performance is by means of parallelisms. So you can use the parallelisms at the system levels. So when you just go for parallelisms, I think we already discussed, right? We may have a multiple processor and we have a multiple disk. So there it won't be a problem at all. Okay. So when you have MIMD, this is MIMD. So when you have an MIMD, so parallelisms can be easily achieved. Sometimes, right, this one, spreading of data across many disks for parallel reads and writes will enable the data level parallelisms. This is something like an SIMD, single instruction, multiple data. So what we can do is, right, we have many processors will be there. So the data will be distributed everywhere. And accordingly, a data analysis assume that this is going to be a matrix. Maybe row 1 will be sent it over here, row 2 will be here, row 3 will be here. So it will be distributed, and thereby, right, we are trying to achieve the data level parallelisms. So by means of parallelism, that is either the task level or the data level parallelisms, the performance of the system can be improved. The other one is the request level parallelisms. So this we also seen, okay? So when you just go with the request level parallelisms, this is also, this may comes under MIMD, right? So this all comes under MIMD architecture. The major important thing is when you just go with the instruction level parallelisms, again, when you just go a little bit deeper, because TLP and the DLP is like a broader view, and they are going for some more below is the ILPs, the instruction level parallelisms. So when you go for instruction level parallelisms, so how to achieve instruction level parallelism in uniprocessor is going to be a big question. So the solution for that is, you know this, right? It is nothing but the pipelining. So when you want to achieve parallelism in uniprocessor, it can be done with the help of pipelining. So you know about pipelining, which is clearly is a overlapping instructions. What is overlapping? This one, right? So fetch, decode, execute. So instruction 1 is here, instruction 2. So this they are saying it as a overlapping. But when they are designing the pipeline, what the insight they have taken is this what? Not every instruction depend on its immediate predecessors. Suppose if instruction 1 is depend on instruction 2, what will happen? Until instruction 2 execute, instruction 1 can't be executed. Okay, so that is the problem. But if suppose if there is a dependency, we can't do anything. So probably right, we need to wait for some times. Okay, so this is the insight they have taken, that not every instruction depend on its immediate predecessors. Okay, so most of the cases it is possible to execute the instruction completely or partially in parallel. Sometimes if there is a dependency, so at that time, right, we cannot execute in parallel, so it has to wait over there. Okay, so if you want to execute ILP in uniprocessor, it is done with the help of pipelining. Yeah. Next, data level parallelisms. I don't know. I think you read this in CO. Have you read this?
Yes, ma'am.
I guess I don't know. You need to explain it. So how here data level parallelism is achieved in set associativity cache? So clearly, it's they have used multiple banks of memory that are typically searched in parallel to find the desired items. Okay, so normally, right, when you just go with the cache, I think it will be divided. Some cache line, I'm not sure because I read long back. So some cache lines will be there. Uh, so based on that, it may work. Okay, or else I will get back to you these things later. Okay, so one is using set associativity cache, data level parallelism can be achieved. This you know, right? Carry look ahead logic. So just now, I mean, you read in your digital. So what is happening? Normally, right, whenever you're just doing computations, uh, so you, assume that if it is like this, 0, 1, 0, something like this, so this carry bit has to be dependent on the sum bit. So until this completed, this carry bit it can't predict. So like that it may be, but with the help of carry look ahead, so probably right we can try to predict this carry earlier, and all can be done simultaneously. Okay, so again, right, this is also a kind of parallelism which is used for speeding up the computing problems. I think these things we will study in deep when you just go with the next chapters. Okay, so but just keep remember parallelisms will helpful for improving the performance of the systems. The next one is the principle of locality. Uh, I think I don't know whether you read this also. Just when you go for the principles of locality, um, see, suppose if you have a memory, if you have like as in 3 GB program you have, and you have 1 GB, and you are loading 1 GB data. Okay, let it be just we are splitting, and we have like this. Okay, 2 GB, and now we need to have this third GB to bring it over here. So when you are trying to bring, now the question is whether we need to remove this or whether we need to remove this, because some replacement policy should be there, right? You got my question or not? Clear. This is your application, which is of 3 GB size, but your memory is of like only 2 GB. So 2 GB has been loaded. So when you want to bring back with another GB here, 1 GB has to be moved off. So we have to go with the replacement policy, which has to be replaced. So what there might be some assumption. So what they're saying is the program tend to reuse data and instructions they have used recently, which have been assume that this is for example, this is 1 and 2. So this is recently used. Since it is recently used, they got the assumptions maybe in later case this may be again used. So what they will do, they will remove this and they will try to put this here. Okay, so that's what they are trying. I mean, some means of way we need to predict uh, I mean, which block has to be there onto the memory. So we have some wide rule of thumb rule, that is 90 by 10, which is what a program spends on 90% of the execution time in 10% of the code. Okay, that is very important. So when you just go for locality and predict with reasonable accuracy instructions and data a program will use in near future based on access in the recent past. So I mean, if suppose if you're just going to remove in any instruction or data, based on the access in the past, based on that, right, we need to go for the things which has to be there. So for that, right, they are going for two things. One is temporal locality, another one is spatial locality. Temporal localities, recently accessed items are likely to be accessed in the near future. So this is the assumption. So whichever the data that has been accessed recently, sorry, or to be accessed in near future. In that assumption, what they will do, so they will keep those data here and they will keep the, I mean, whatever the data which is not accessed, so those things will be removed from the memory. That is one cases. The other cases is spatial locality. In this case, items whose addresses are near one another tend to be referenced closer together in time. So something, assume we have this. Suppose we have data of like 2020 like this. So if suppose 1010 has been already there here, something is there 2002 2010 is also there in that. So okay, so now right, if from 1010 to 2020 has to be comes to here, so now the question is which has to be removed, whether we have to take this or we have to take this. So according to spatial locality, whose addresses are near one another tend to be referenced close together in time. So with that assumption, they will remove this and they will try to put this. This is for spatial locality. Temporal locality is associated with the time. Okay, so these two things are very important. Even they will say with respect to arrays. Uh, I think right. Suppose if you are defining an array, assume like a two-dimensional array, you might have heard two things, right? One is the row major order, another one is column major order, right? Is there any difference between these two things? Guys, is there any difference in row major and column major? Guys, are you there?
Yes, ma'am, that's the difference.
Yeah. Tomorrow you find out right what is row major and you know it right what is row major and what is column major order. And many times right they may say, yeah, I will give the answer. Many times they may say row major order will be more suitable than the column major order. Can anyone say why? So this is row major, right? Suppose you have this, okay, 0 1 0 okay, 0 0 0 1 0 2 0 3. Similarly, right? Okay, 1 0 1 1 1 2, so on so on. Isn't it? So row major means it will be stored like this. First is 0 0 will be there, then 0 1 0 2 0 3, and then 1 0 1 1 1 3. It will be like this for row major. When you go with the column major, it will be like what, 0 0 1 0 2 0. Assume it is the case. Next 0 1 1 1 2 1. This is the column major, isn't it? So which is I mean with respect to principle of locality, which is good actually.
Row major.
Yeah, actually, row major order is correct thing, right? Because what is happening when you are going to fetch the data from the memory, what will happen? It will be fetched. It won't fetch like a single thing because the data will from RAM is fetched and it will goes to the cache memory. When it goes to the cache memory, it won't go as byte alone. So it is a set of bytes. When it is a set of bytes, like contiguous memory, it will go as contiguous memory. So when it is a contiguous memory, probably assume that if it is going to be 4 bytes, so these four things, four data will goes to the cache. Even our program, when you are trying to write, most of the things will be like this, right? You will try to access this, and then more probably will try to do it. Okay, so such cases, right? We can just row major order will be the best things. Or else, what will happen? Every time you will have a catch miss, right? See, it will be like this 0 0. Suppose if it is a column major order, it will be like this 0 0 1 0 2 0 3 0. After fetching, I'm fetching 0 0. I need now 1 0. So what will happen now? See, sorry, 0 1. It is not, it won't be in the cache. Immediately it will be flushed. You understood? It will be flushed. Now what will happen? 0 1, 1 1 2 1 3 1 will be get. After fetching 0 1, now I need what? 0 2. So immediately this again it will be flushed and again 0 2 will comes. That's the problem. That's why, right? Row major order. And again this depends upon the application also. You need to decide accordingly. Okay. So that's what the principle of locality plays a vital role with respect to the accessing. So because if the data is readily available, probably the performance may be improved. So that's what they are trying to say here. Okay. I think we will continue this in the next class, the next common case. I think, so with that, chapter 1 is over. So by Saturday, chapter 1 is over. Next Saturday, we will have a test. So I will forward to this in our class group. So if you have any doubt, you can ask me.